Some materials are able to conduct thermal energy faster than others. If a material is a good conductor of thermal energy, this means that the heat energy can traverse from one side of the material to the other in less time than it would if the material was a poor conductor. And with these two materials here, I've surrounded them with some insulation material so that very little heat energy escapes into the environment. So what are some examples of good and poor thermal conductors? Generally, anything that can conduct electricity well, for example metals, are good heat conductors. Whereas insulators of electricity, for example plastic, wood and rubber and so on, are poor heat conductors. Now this better conduction in metals is partly due to the presence of free electrons. Now, free electrons are the electrons that are not bound within an atom. In fact, they're free to move through the crystalline metal lattice. When these free electrons absorb heat energy, they gain kinetic energy and move much faster. And their kinetic energy can be transferred to the metal atoms, making them vibrate more vigorously. And these vibrations pass from atom to atom, transferring heat energy in the process. Insulators also transfer heat energy through thermal vibrations in their nanoscopic structure, but they do not have the added benefit of free electrons to speed up the process. Now, of course, material science is far more complex than this, but this gives you a higher level overview of what's happening at the nanoscopic scale. So what about liquids and gases? Do they conduct thermal energy? Well, they do conduct thermal energy, but they are rather poor conductors. In fluids, heat transfer happens faster through the process of convection. In other words, heat transfer that occurs from the macroscopic movement of the fluid. And we can see this in the diagram here. Now, the measure of how well a particular material conducts heat energy is described by the coefficient of thermal conductivity, and this value depends on the material's properties. So this coefficient has units of joules per second per meter per degree Celsius, and the higher this value, the better this material is at conducting heat. But we also have three other factors that affect the rate at which heat is transferred through a slab of material. So let's introduce this diagram here so we can visualize what these other factors may be. So on the left-hand side, we have a volume at a constant temperature, and we've called this temperature T subscript 2. And on the right-hand side, we have a volume of cooler temperature at T subscript 1. Now this could be the difference in temperature between the air outside on a hot summer's day and the cooler air inside a house. And this material here could be part of a glass window. So heat energy will move through the glass from the higher temperature region to the lower temperature region. The larger the cross-sectional area here of this glass material, or whatever material we have, the higher the rate of heat transfer, because the number of atomic collisions between the outside and the material surface increases with a larger area. Now the thickness of this glass also has an effect on the rate of heat transfer. Heat transfer from the left side to the right side is accomplished by a series of molecular collisions. The thicker our material, the longer it will take to transfer the same amount of heat. Lastly, the temperature difference between both ends of the material plays a role here. A higher temperature difference results in a larger rate of heat transfer, and the temperature difference is simply the temperature of the hot region minus the temperature of the cold region. So if the temperature between these two regions was the same, there wouldn't be any heat transfer. So we can write the rate of conductive heat transfer through some material like so, where Q divided by T is the rate of heat transfer in watts or kilocalories per second. So let's make use of this equation now with a real-life problem, which you've probably experienced yourself in the past. So it's a hot summer's day and we're storing some canned drinks in a styrofoam ice box. Now the total surface area of this ice box is 1.5 meters squared, and the average thickness of its styrofoam walls is 3 centimeters. Inside this styrofoam box, we have a bag of ice and the canned drinks, and the temperature inside is at 0 degrees Celsius or 32 degrees Fahrenheit. And to keep everything cool inside, the ice uses up the surrounding heat energy during its phase change, and we talked about phase change in the last lesson. The surrounding atmosphere outside the box is at 35 degrees Celsius or 95 degrees Fahrenheit. And lastly, the styrofoam itself has a thermal conductivity of 0.01 joules per second per meter per degree Celsius. So we want to find out how much ice melts over an 8-hour period. In other words, how much ice do we need to keep all our drinks cool over this 8-hour period? Okay, so let's write out our known variables. Now, what do we need to find out? We need to find out the amount of ice needed in kilograms before all of it melts over the 8-hour period. And we need to know how much heat energy will be transferred through the walls of the icebox over this 8-hour period. So how can we start to solve this problem? From a previous video, we learnt that when ice is at 0 degrees Celsius or 32 degrees Fahrenheit and is absorbing heat energy, then the temperature of this ice remains constant during this phase transition. In other words, when it's melting. So first, if we find out how much heat energy will enter into the box over 8 hours, we can use the latent heat of fusion equation, which we looked at in the last video, to find out the mass of ice required to absorb all of that heat before its temperature starts to rise. And its temperature will only start to rise when it's fully converted into water. So next, we need our equation for the rate of conductive heat transfer. So we're not really interested in how much heat is being transferred through the walls of our icebox every single second. We want to sum up the total amount of heat transferred over an 8-hour period. So because we know the time over which the heat transfer takes place, we can multiply both sides of the equation here by the time variable to isolate the heat. And when we sum up all our values here, we get 504,000 joules of heat energy. And we've rounded this down to 2 significant figures because the accuracy of our thermal conductivity is only good up to 2 significant figures. So we've got about 500,000 joules of energy being transferred into our icebox over 8 hours. Now the latent heat of fusion of ice is 334,000 joules per kilogram, and this is the amount of energy that must be supplied to a kilogram of ice to completely change its physical state from a solid to a liquid. So because we've got the total amount of heat energy and we've got the latent heat of fusion for ice, we can rearrange this equation and find the mass of ice required to keep our drinks and the inside environment of our icebox at 0 degrees Celsius for the entire 8-hour period. So when we divide these two values together, the mass of ice is 1.5 kilograms or 3.3 pounds of ice. And again, we're using two significant figures here because the accuracy of the heat energy in the last equation is only good up to two significant figures.